In section 10.2, we'll be continuing our talk of the gas laws, and we'll continue with Charles's law and Gay-Lussac's law. We'll also be covering what a Kelvin is. So let's start with that, Kelvin. Since it's a very important concept for our next laws, we're dealing with temperature, and actually Kelvin is a unit of temperature. And it's actually very similar to the Celsius scale because a change in 10 degrees Celsius is the same as a change in 10 degrees Kelvin. They're worth the same amount, but what's different here is the scale that we're dealing with. So Celsius is actually defined by the freezing point and the boiling point of water. So back a long time ago, whenever we were deciding on the scale for all these different temperatures, scientists took water. It's very important for life, and so they measured the temperature at which it froze, and they set that at 0 degrees Celsius, and then they measured the temperature at which they boiled, and that was set to 100 degrees Celsius. And then everything else was just split up into 100 equal segments, that whole section from 0 to 100. And so that's how they come up with the definition of the Celsius. Now, the Kelvin is a little bit different because it doesn't really care about water. What Kelvin is measuring is the temperature from absolute zero. And in physics, what absolute zero is, it's the temperature when there is no molecular motion in a substance. Remember when we talked about kinetic theory and we talked about temperature being the measure of kinetic energy of a substance? Well, when there is absolutely no motion, that is what we measure as absolute zero. So if we can go back to the simulation from last time, we can see that in action, or actually not in action. So actually, this is what we're seeing: a still shot. My molecule is not playing. Not my molecule. My simulation is not playing at all. And so this is what absolute zero would look like, just absolutely no motion. So if I press play on this and my molecules start moving, this is some temperature. I really don't care what it is. But if I were to pause that and all the molecules stop moving, this is now absolute zero. In theory, at least, because absolute zero has never been observed by scientists. The coldest we can get any substance to is liquid helium, and it's been recorded at 0.3 Kelvin. And so that is the closest that scientists have ever come to seeing absolute zero. It's not seen anywhere in the universe. It's only seen in our labs. And the coldest we can get it to is 0.3. We can't get to that perfect absolute zero. Right, coming back to this, we need to understand the Kelvin, because when we're using our gas laws, we'll be seeing that in the next two, we are actually dividing by our measurement of temperature, and this gives us a problem mathematically because, well, 0 degrees Celsius is a valid temperature. It's a real temperature. If we were to use it in our formulas, it would actually break our formulas because we can't physically divide by zero. It's a mathematical impossibility. So we'll be seeing that in a little bit more detail in just a second when we pull up to an example. All right, so now how are Kelvin and Celsius related? Well, you can see that in this graphic, and I'll pull up these graphics too, but let's base it off the freezing point of water in Celsius, that is 0 degrees Celsius. But in Kelvin, we can measure that as 273 Kelvin instead. And so this makes our conversion a lot easier because it's just a simple addition problem. So if you have some temperature in Celsius, so in this case 0 degrees Celsius, to measure in Kelvin, you would just add 273 to it and call it Kelvin. And then if you start in Kelvin and want to work your way backwards into Celsius, then you do the opposite, where we have our temperature in Kelvin and we subtract 273 from that. So let's practice on that and see how it actually works. So say that we have this temperature 180 Kelvin, and we want to know what it is in Celsius. Well, if you look to your formulas, let's do this one, Kelvin to Celsius. If we have our temperature in Kelvin, all we have to do is subtract 273 from it, and we get the result of negative 93 Celsius, which, yes, we can measure temperatures in Celsius, but they can be negative. When it comes to Kelvin, we cannot go past zero. So a negative Kelvin temperature is physically impossible. So you can use that as a check to know if you've done the problem correctly. And let's compare two different temperatures now, 400 Kelvin and 180 degrees Celsius, which is hotter? Well, it's pretty simple, right? 400 is the bigger number, so we'll say that 400 Kelvin is hotter. But this gives us a little bit of a problem because we can't compare these two units of temperature directly. We have to convert one into the other. They have to be the same unit so we can compare them fairly. All right, so we can start with just a simple conversion. Here are the formulas. Again, it's just a matter of adding or subtracting 273 depending on where you start. So we start with our temperature in Celsius. All we have to do is add 273. Remember that example of freezing water. 0 degrees in Celsius, but it's 273 in Kelvin. All right, so this is why we're adding 273. So my new Celsius temperature, 180 degrees Celsius, is the same as 453 Kelvin. And now you can compare them directly. So 453 is higher than 400. So actually, this temperature is the one that is hotter. And we can also compare it in the opposite way. If we want to take our 400 Kelvin and know what it was in Celsius, you'd have to do the opposite calculation, subtract 273 from it. Remember that 273 Kelvin is 0 degrees Celsius. That's why we're subtracting. When you do that, 400 minus 273 gives you the result of 127 degrees Celsius. So again, when you do it that way, the second temperature is the hotter one. And this actually gives us a little bit of trouble for when we're talking about standard temperature and pressure, because as we saw in the last section, we learned that the pressure is 1 atmosphere. Nothing changes. We haven't talked about pressure again. But the temperature, in this case, we set it at 0 degrees Celsius as our standard temperature. But as we just learned, we can't use Celsius in our formulas that are coming up next. So in this, the only adjustment we have to make is that when you're given 0 degrees Celsius or your standard temperature, all you have to do is add 273 to it. So now our new standard temperature is really 273 Kelvin that we'll be using in our formulas. So I just wanted to bring this up and make sure that this one doesn't trip you up when you see it in a problem. With all that temperature talk out of the way, let's go ahead and look at the next gas law. In this case, we have Charles's law, and this is named after the French scientist and hot air balloonist Jacques Charles. And so now this gas law that we're looking at will describe the relationship between temperature and volume of a gas. And a good example of this is a hot air balloon, because if you know how a hot air balloon works, what's going on is that it's not like a party balloon that's filled with helium and that's what's holding it up. But this balloon is filled with regular air that has been heated. And when that happens, the air inside actually expands and reduces its density. And so now we have, in this balloon, we have low density air as compared to the air on the outside. And it's this different in density that holds the balloon up. And that's exactly what Charles observed, is that when gases are heated, they expand. You don't add more gas and you don't lose any of it, but what's going on is that it takes up more room. And again, when it comes to hot air balloons, this is what creates lift. And then the opposite holds true, is that when they are cooled, gases will reduce in size. They'll become smaller and they become compressed. And so a good graph on here is right here. Where as you increase the temperature, so does the volume. And you can think of it the opposite. As you lower the temperature of a gas, the volume will decrease with it. And so this type of mathematical relationship is called directly proportional. If one of these values goes up, the other one will too. And if one of them goes down, it will fall as well. So that's the idea of Charles's law. Now let's look at it in terms of math. So if we want to use symbols on it, we can say that V over T is equal to K. And in this one, V is my volume, T is the temperature, and again, this is measured in Kelvin, actually I converted from Celsius. And then K is my constant. In this case, it's just my result. Because if I were to pair two of these systems together, I can actually track the change in the volume and temperature of two different gases, or I should say the same gas in two different times. So it's what my formula looks like when I have two sets of properties, where I have V1 divided by T1 is equal to V2 divided by T2. So in this next slide, let's actually see it in action and see what that is all about. So a problem that you might see will look something like this, that at a constant pressure, a sample of gas occupies 420 milliliters at negative 40 degrees Celsius. What volume does the gas occupy at 0 degrees Celsius? And so what's important here is that it tells me that I have a constant pressure, which means that I don't need to worry about it in my formula. That makes things a little bit easier for me. So now, from this problem, I need to be able to draw my information and make sure that your volume and temperatures are paired in the right way. So in this case, I'm starting with 420 milliliters of a gas. That is my volume. And then it is at negative 40 degrees Celsius. That is my first temperature. And notice on here that my temperature in Celsius, again, I can't use that in my formula. If that was 0, that would break my formula. So I have to add 273 to my temperature in Celsius to give me my new temperature of 233 Kelvin. Okay, so that is all well and good. That's all set up. So now what are my V2 and T2 values? If I keep reading the problem, let's see. The question is, what is the new volume? So my volume at this point is unknown, but my new temperature will be 0 degrees Celsius. And again, there's that problem. If we were to put this into the formula, it would give us an invalid answer, and we'd be done with that. So to fix that, we need to add 273 to the temperature, and so my new temperature, T2, will be 273 Kelvin. And with this out of the way, I now know 3 out of 4 variables, and I'm ready to solve this algebraically. I have my expression right here of V1 over T1 is equal to V2 over T2. And I can fill in the things that I know, where my V1 is 420 milliliters, and I divide that by 233 Kelvin. On the right side, my V2 is unknown, but my T2 on the bottom is 273. From this, I will multiply both sides by 273 so that on the right, my 273 is canceled, and on the left, the 273 moves to the top. So now I have 420 milliliters times 273 Kelvin divided by 233 Kelvin. And notice the two units that are matching on this one, top to bottom, Kelvin and Kelvin will cancel out, and I am left with milliliters. If you do this through a calculator, the result that you get is 492 Kelvin. All right, and that's pretty much all there is to these Charles's Law problems. If you know how to work with your variables and how to solve for the unknown, then they're very simple, straightforward problems. I really think the hardest part of this comes from grabbing the information from the problem and setting it up in the right way. Next, it is Gay-Lussac's law, and so this law is named also after a French scientist named Joseph Louis Gay-Lussac. And so what he observed was the relationship between temperature and pressure. Remember that in the last one for Charles's law, we did volume and temperature, and in this case, we're doing pressure and temperature. And again, the volume is constant, so a lot of the times you'll see something like the problem will tell you that it's a rigid container. That means that the volume is not changing, that we have a constant volume. All right, so now what he observed was that when the pressure of a gas is increased, when you're pushing down on it, then the temperature will rise. Or you can say it the opposite way. When you heat up a gas and it is an enclosed container, then the pressure inside of it will increase. And so you actually see this in your tires a lot. So if it's a very hot day in the summer and you measure your tire pressure, you might notice that it looks a little bit higher than what it was the day before when it was cooler. So it's because gases, again, we saw in Charles's law that they expand when they are heated. So now you have a larger gas in the same amount of space. And so it's what's going to increase your pressure. Think of pressurized air in that way. All right, then the opposite is also true, is that when gases cool off, then their pressure will decrease as well. And again, going back to the tire example, in the wintertime, you need to fill up your tires more because the air pressure inside of the tire has dropped. You didn't actually lose much air, but because the weather outside is colder, that means that there's less air pressure inside of your tires. And so on a graph, you could call this, again, a directly proportional relationship, just like Charles's, because that means that as you increase the temperature, the pressure of it will increase as well. And if you lower the temperature, then the pressure of it is low as well. So again, what you do to one variable the other one will do exactly the same, either increase or decrease. All right, so now looking at this mathematically, we can see it as this, that the pressure over the temperature is equal to K, my constant, my result. All right, and so when we link a gas at two different sets of properties, they will actually come out to be the same result. So algebraically, we can link them together in this way, where my P1 divided by T1 is equal to P2 divided by T2. So let's go ahead and look at an example of that and see what it's like. So a problem that you might see will look something like this, that a sample of neon gas exerts a pressure of 120 kPa when the temperature is 400 Kelvin. What pressure is produced when the temperature is raised to 600 Kelvin? All right, so again, the trick in all these problems comes from reading the problem and grabbing the right information from it. So this one, I know that my P1, my starting pressure is 120 kPa, kilopascals, and my temperature to go with that is 400 Kelvin. Notice in this one that they already gave me the temperature in Kelvin, so I don't need to change anything. I don't need to add 273 with it. So now for my second part of the problem, it's asking what is the new pressure. So my pressure is unknown, but my new temperature becomes 600 Kelvin. So again, in this case, I know 3 out of the 4 variables. I can plug them into my equation and solve for the unknown, where I have P1 over T1 is equal to P2 over T2. So now on the left side, I know that my P1 is 120 kilopascals, and that is set over 400 Kelvin. And I can set that equal to P2, that is the unknown, over my new temperature, 600 Kelvin. So I can go through this and solve it algebraically again. So I have the 600 Kelvin. On the right side, I need to get rid of. So if I multiply both sides by 600 Kelvin, on the right side, it is canceled, and 600 Kelvin is multiplied on the left side. So my expression is 120 kilopascals times 600 Kelvin divided by 400 Kelvin. And notice that on this one, again, my Kelvin, I have one on top, I have one on bottom. They're matching, and so I can cancel them out. My final answer will be set in kilopascals. And so if you carry this calculation in your calculator, you get 180 kilopascals is equal to my new pressure. And so in summary, what we have here is the three main gas laws. We have Boyle's law, Charles's law, and Gay-Lussac's law. And notice that Charles's law and Gay-Lussac's are actually very similar to each other. They both show a directly proportional relationship from temperature. I think that makes it a little bit easier. So whenever you're given a temperature, you'll know that it has to be divided. It has to go on the bottom. The only difference between these two laws is that Charles's deals with volume and Gay-Lussac's deals with pressure. Now, when it comes to Boyle's law, it completely ignores the temperature, and this is just it's the opposite relationship than the other two laws, where we have an inversely proportional. This means that if I raise my pressure, my volume will drop, or if I raise my volume, then my pressure will drop, and vice versa. All right, so keep this in mind. I think it's a very useful way to keep them all separate and know they're similar, but there's a slight difference between them. So in this next section, we'll be looking at the combined gas laws, and we'll be looking at ideal gas laws and adding our last property of gases that we can measure and track and calculate.